Hello everyone, great to be with you again, and in this lecture we are going to discuss how to use the conceptual model approach in GMS to build regional scale models. Up to this point, all of the models that we have been dealing with have been very simple models with very simple geometry and sources and sinks and features, and now we're going to give you the tools to build more realistic models of complex aquifers with complex data. Basically, in GMS there are two different modeling approaches. The one that we've been using thus far is called the grid approach. And what we do is we first build a three-dimensional grid, and then we select the cells of the grid and assign properties such as hydraulic conductivity, top and bottom elevation directly to the cells, or we select a cell and assign sources and sinks to it, such as drains or wells or general head conditions. And this works great for simple models. It's worked just fine for us, but you know, if you have a really complex region with a complex stream network, for example, or hydraulic conductivity zones, irregular boundaries, this can become really tedious. And so for those cases, we use what is called the conceptual model approach. And in a nutshell, we build what we refer to as a conceptual model inside GMS, and it consists of GIS features such as points, lines, and polygons, and then we assign the properties directly to this grid-independent conceptual model. And then, after that's all set up, we create a grid, and then the features and geometry, sources and sinks, properties are automatically converted from the conceptual model and assigned to the individual grid cells. And so you just focus on setting up these points, lines, and polygons, defining the aquifer shape and properties, and then all the work involved in assigning that to individual cells is done for you automatically. So it works great, especially on complex regional models. Conceptual model approach consists of 5 basic steps, each of which we will discuss now in detail. We build a base map, define a projection, select our units. Those first 3 are pretty trivial. And then build the conceptual model, which is where most of our work takes place, and then convert that to our grid-based numerical model. So first of all, establish a base map. So this something we haven't done much yet. We've been working in local coordinate space. Well, now we need to build a model at a specific location with specific features, and it's aligned with rivers and lakes and outcroppings and things like that. So in order to really support and facilitate this model building process, it really helps if you have a base map. And it used to be that we would get a digital map and then go through a 3 or 4 point registration process to put that properly scaled in the background. But now it's quite easy with web services. So if you go into the File menu and you select Add Online Maps, this uses an Esri web mapping service, and it creates a dynamic base map that refreshes when you pan or zoom. So once you've made the connection, if you zoom in, it will go retrieve a higher resolution version of the map and display that in the background. So that's what I'm showing in this screenshot here is an Esri base map. So once you select this Add Online Maps command, it brings up the map locator. This is actually well, this is powered by Esri, but it allows you to do a search. So you can zoom out and have a view of the whole world, and then zoom in on your region of interest, and that actually, you know, takes just a few seconds. That's typically what you would do. Or you can also type in a location and do jump to search location, and it'll zoom in. So in this case, my university, Brigham Young University, is located in Provo, Utah. So if I type in Provo and hit jump to search location, it'll zoom right in. So once you've zoomed in, then you click OK, and it takes you to this window. And here is where you select what base map you want. And there are a number of options. I often use the World Street Map in the lower left corner, or World Imagery. And by the way, you can run this multiple times and have multiple base maps loaded to GMS, and you can toggle between them. You can turn them on or off independently. And so sometimes it's nice to switch between a street map and an imagery. But there are a lot of options, and I would encourage you to play with that and find ones that you like. And again, as I mentioned, once you select your map and click OK, it loads in the background, and then over in the Project Explorer window, there's a GIS Layers folder, and your map will be listed under that folder, and you can toggle it on or off. Sometimes depending on your internet connection, zooming in and out or panning can take a minute for it to refresh. And so sometimes, depending what you're doing, it's useful to turn it off so that your screen refreshes a little quicker. And if you do this multiple times, the different maps will be stacked right here in this list, and you can again toggle their display on and off to switch between them. So that works out really well. Now, as I mentioned, every time you pan or zoom, it sometimes there's a lag as it goes to refresh that base map. That can be time consuming, especially if you have a limited bandwidth internet connection. So what you might want to do is pan out to where you see the full range of the base map you're likely to want to view. And then if you right click on the base map and select export, it'll bring up this dialog in the lower right, and if you click OK, it will create a local tiled base map. And when we say tiled, what it does is it saves several different versions of the map at different resolutions, so that when you zoom in or out, it chooses which one to render based on how far in you've zoomed in or out, so you get the most crisp image. And the refresh is lightning fast. Honestly, I highly recommend doing this. Once you find a map you want, it saves the copy of the base map to the same location as your project file. And every time you reopen it, it will load that base map. It's a great option. And while we're on the topic, in addition to the base maps, you can there's an option in GMS to import other kinds of data as well from web services, such as DEM, soil maps, land cover maps. And you go through the same process, but once you've established your base map, you don't need to do the map locator. It takes you right to this window here, and I've expanded it to show all of the options. And these change from time to time as they add more features, but again, you can get your base maps that we saw before, but now you can access land cover databases. So these are rasters. This worldwide elevation data, this is basically a digital elevation model that you can then interpolate to your model. For example, if you want to generate your top elevations for your MODFLOW grid, you'd want to do that from a DEM. There's an ArcGIS world terrain base, soil type shapefiles, all kinds of great features that you can download and access directly off the web. It's a really great asset when you're trying to build a model. Okay, step number 2, select a projection. If you go to the display menu and select the display projection command, this will bring up the display projection dialog where you select a projection. And this defines the default coordinate system for your project. If you have, and then when you import data with, let's say, a different projection, knowing what your preferred projection is, it will automatically display it in the correct context. Now, when you set up your base map, it will prompt you to select a projection. And so in most cases, once you do your base map, you don't have to go in and redo this. In 99% of the time, I'd recommend you just select the default global projection that comes with your base map. And so, this is generally something that happens implicitly, but I thought I would mention here that establishing a projection is part of this overall process. And then again, selecting units. If you go to the edit menu and select units, the length units are generally tied to your projection. And so when you select units, length and time are the ones you typically have to worry about. The rest of them are only important if you are dealing with a contaminant transport model in general. And what this does is when you go to input some values, such as the case shown in the lower right, it displays the units that you should be using next to the input, where you input the parameters of your model. So it's your responsibility to convert your inputs to the consistent set of units. So if your length units are feet and your time units are days, then hydraulic conductivity would have to be put in feet per day. Recharge would be in feet per day. Flow rate would be cubic feet per day, and so forth. And that helps ensure that you have consistent units. It does not do unit conversion for you. And your length unit has to be consistent with your selected projection. And so when you click on this dot, dot, dot next to the length unit, it will have you select a vertical and a horizontal unit. And again, that's generally tied to your projection that you have. And so, but that's something that you need to set up early on. Okay, so once we have a base map, a projection, and units, the next step is to build a conceptual model object. And you do that by right-clicking in an empty part of the Project Explorer window and selecting New Conceptual Model. Essentially, what this does is it's this grid-independent representation of the major model features, as I described before, and it allows you to automatically discretize the model input for MODFLOW. And it's also a way of organizing all of the layers of information associated with your conceptual model. And so just in terms, what does this mean in general? It's best illustrated through a simple example. Suppose you have a site that you want to model, and I've picked an extremely simple model to illustrate this. So you may have a reservoir with a well and a river and a lake, and then an irregular boundary. when you build a conceptual model in GMS, you basically recreate this in the model, and so it would look something like this. As I cycle between those, you can see the parallelism there. And so first of all, we have a polygon for the overall model area. We call that a variable head polygon, meaning that that's where we're going to solve for heads. It's the active region of your model. We have a general head polygon here in the middle to represent our lake. We have river arcs. Arc is the term we use for polylines. And these define both the geometry and the properties of the river. And then down where the lake forms the lower boundary to the model, we have specified head arcs. And then we have a point where this well is located. And then again, on all of these features, we define hydraulic conductivity, the conductance of the general head polygon, the river arcs, the stage, the bottom elevation. Everything is assigned directly to this, independent of the grid. And then we create a numerical grid, overlay it with this conceptual model, and then as you can see by the symbols, the properties and the geometry of these conceptual model objects are automatically transferred over to our grid-based numerical model. Now, one of the beauties of this is, well, first of all, the main benefit here is it alleviates you from having to compute and enter each of these individual cell-by-cell values. If we were doing this by hand, we would have to compute an individual conductance for each reach of the cell that overlaps, of the river that overlaps a cell, and then calculate the stage and river bottom elevation. And if the stage varies as you go down the stream network, so that can be very tedious. But so it does all that for you. Another benefit is if you do it once and decide later that you want to have a grid that has twice as many rows and columns, building a new grid and rediscretizing things to the grid cells takes literally a few seconds. So it really is a incredibly efficient way to do this. And we developed this years ago in GMS, and then other competing MODFLOW GUIs have tried to copy this over the years, but this has really been one of the prime features of GMS, and something I think GMS does better than any of the other products. So in order to build our conceptual model, we have to be able to interactively create and edit these GIS feature objects. And so let's talk about the types of feature objects supported in GMS. If you're familiar with ArcGIS or QGIS, a lot of these concepts will be somewhat familiar to you. I would argue that it's way easier to build feature objects in GMS than it is in either QGIS or ArcGIS. And so we start out with points. This would be like a point feature class in ArcGIS. Points can have attributes depending on what you're trying to represent with them. For example, if we use a point to define a well, then one of the features would be the pumping rate for the well. Or excuse me, one of the attributes. We also have what are called arcs, and arcs consist of the endpoints of the arcs are called nodes, and the midpoints of the arcs are called vertices. They're different because you can assign properties to the nodes at the endpoints of the arc, and then typically we assume that those properties vary linearly along the length of the arc. For example, if this arc were to represent stream reach, I could define a stage at one end and another stage at the other end, and then we assume that the stage varies linearly along the length of the arc. But you can also assign features directly to the arc itself that are applied to the entire arc, but anything you want to potentially vary along the length of the arc would be assigned to the nodes. And the vertices, on the other hand, they function solely to define the geometry of the arc. the trajectory. Now, if you want to take a long arc and assign a node somewhere in the middle, you can right-click on a vertex and convert it to a node, thereby splitting the arc into 2 arcs. And the point is, you can choose exactly where you want to split your linear features up into where the nodes are located so that you can adequately assign properties wherever you need to. And then, finally, if you create closed loops defined by a set of arcs, those become polygons. And I don't have the vertices highlighted here, probably should have, but to create a set of polygons, you just start connecting your arcs, and they automatically, when you're digitizing these by clicking on the screen, they'll automatically snap together when you get close, so it's quite easy to build these. And then there's a build polygon command that will convert these closed loops into polygon features, which you can select or double click on each of these polygons and assign attributes directly to the polygons. So those are the main features that we're working with. So let's talk about, now we're going to break down building a conceptual model to a series of individual steps, and we're going to start out at this level. First of all, you need to build a conceptual model object, and again, this is used to organize your conceptual model data, and it consists of one or more layers of information, which we call coverages. Each individual coverage is a set of points, lines, and polygons. So, for example, you could have a coverage for wells, and one for hydraulic conductivity polygons, and one for your river network, and those are all categorized or organized underneath the conceptual model. So when you select this command, it asks you for the name of the conceptual model, and you can actually associate this with different models in GMS, but by default it goes to the MODFLOW package. And then the next step is to build your coverages. And so to build a coverage, and I just described what a coverage is, but so you right-click on the conceptual model and select New Coverage, and that will then create a new coverage underneath that conceptual model object. And again, you can use as many of these as you want. In some cases, you can put your entire model into a single coverage. In other cases, you're going to have a large number of coverages. And when you create new coverage, it brings up this coverage setup dialog. And what this allows you to do is define the types of properties or objects that you're going to be putting into the coverage. For example, in this case, on the left-hand side, sources, sinks, boundary conditions, the user has selected wells, drains, and river objects. And you'd have to scroll down to see if there's anything else selected. But once that is established, and you'd probably want to name your coverage something to help remind you what it's for. Then when you go to create objects in the coverage, it allows you to assign attributes associated with wells, drains, and rivers. And so on the left, these are generally assigned to points and lines, although you can assign them to polygons as well. For example, you can have a general head polygon or a drain polygon. But then this set of objects, options in the middle, these are, it says aerial properties, so these are always assigned to polygons, and these are generally things associated with MODFLOW arrays. So hydraulic conductivity, specific storage, top and bottom elevations, those can be assigned through a set of polygons inside a coverage. Now, by the way, you can only have one set of polygons in one coverage, so that each polygon defines a unique area. So if you have one set of polygons defining your hydraulic conductivity and a different set defining your recharge, you need to put those into separate coverages. And over on the right, we have observation points. It's kind of a special type of coverage associated with model calibration, which we'll talk about later. And then down at the bottom, a few things to note. This default layer range, if you set that 1 to 1, then whatever you create is going to, by default, be assigned to layer 1. If you turn on the layer range option, that would allow you on an object-by-object basis to indicate what set of model layers it is associated with. And then this toggle used to define model boundary active area. This needs to be on at least one of your coverages. And generally, I like to do it with my primary source sink coverage, but you have to have a coverage that has a polygon that covers your active area, and then you toggle this on, and it defines the active area of your model. And then the rest of this we can talk about later, but that sets up the primary features of your model. And so again, once you've defined using this dialog what properties or what kinds of objects you're going to create, then when you create an object and then go to edit its attributes, it's going to bring up a dialog that looks something like this. And in this case, we have a set of pumping wells. And so we have the X, Y, Z coordinates, and you can toggle the coordinates on or off. We have the name, and then there's a little selector that defines the well. But so, for example, if you have wells, drains, and rivers, you could change the feature from a well to a drain. You can have a point-based drain if you like. Sometimes we represent a spring as a drain. And then, depending on the type, you get different columns over on the right. In this case, we have a well, we have a pumping rate, and then we have an option to define a top and bottom elevation of the screen of the well. And again, there's this yellow line up top. Anything you enter here will be copied all the way down to all the features. You wouldn't do that for the X and Y coordinates, obviously, but you might want to do it in some of the others. And again, so the contents of this attribute table will change based on the features you have selected. And you can filter it by certain types. You can say, well, only show me my wells. So these selectors at the top allow you to filter what's being displayed. Now, while we're on the subject of coverages and conceptual models, we have to revisit the issue of conductances. So many of the objects in the source sink category that was on the left-hand side of that coverage setup must be assigned a conductance value. So this would be drains, rivers, general head, and so forth. And we've had a good discussion on conductances already, but now we're going to assign conductances in a way such that they can be then transferred over to cell-by-cell conductances. Everything we've talked about so far has been the actual conductance you would assign to a cell. But now we have to do things a little bit different. For arcs, the conductance should be assigned on a conductance per unit length basis. And for polygons, the conductance should be assigned on a conductance per unit area basis. The reason being is you don't need to calculate the length of an object in an individual cell. GMS will do that for you. So we just enter the conductance per length value, and then later when it converts that to the cell-by-cell values, it converts that to a cell-by-cell conductance. And I have some diagrams that will illustrate that. So what we want to do is let GMS calculate the length of an object in a cell or the area of overlap on a cell, and then determine the appropriate cell-based conductance value. So let's dig into this a little deeper. Let's suppose you have an arc, and we've seen a diagram similar to this before. Let's suppose that we are using an arc to represent a river object that will be simulated by the river package. And as was the case before, we have the length of a reach, and in this case I'm just talking about maybe a reach that would go across multiple cells. We have M is the thickness of the riverbed material, W is the width of the river, K is the hydraulic conductivity of the riverbed material, and we have the direction of flow shown. So what we would assign to a cell is K, the hydraulic conductivity, times the cross-sectional area of flow divided by the length of flow. Well, the length of flow in this case is the thickness M, because we're flowing vertically. And the length, the area of flow would be L times W. So that's what, if you were to calculate the length of that reach inside a cell, this is how you'd calculate the cell-by-cell conductance. However, for an arc, we just factor out that length term, and what we enter is K times W over M. And this is the conductance per unit length. So if you then later take this term and multiply it by the length of overlap of that object in the cell, you have the right value. So let's illustrate this with a real-world example. On the left we have 4 cells, 1, 2, 3, 4. And then we have 2 arcs, arc A, that is an arc B. And for arc A, we have assigned a conductance per unit length of 2.5. And for arc B, we have a conductance per unit length of 1.2. And remember, the cell conductance is K times the area of flow. That's the width of the river times LEN, which is the length of overlap in an individual cell. So looking at arc A here, the length of overlap on cell number 2 would be 71.9. So that's right down here, the first row of this table, arc A2 in blue. So these are color-coded to help you match. The conductance per unit length is 2.5. And the length is 71.9. So if you take 2.5, multiply it by 71.9, we get the cell-by-cell conductance. So the cell conductance is the arc conductance times the length, which would give you this cell conductance up here. And what GMS would then assign to the cell is 179.8. Likewise, look at this red section. Now this arc takes a jog right here. We go from arc A to arc B. So it would actually create 2 entries of the river objects inside this cell. And the first one would have a length of 58.9. We multiply that by 2.5 to get this conductance 147.3. And the second one is in arc B, 56.4, but it has a different conductance per unit length. So we multiply 12 times 56.4 and we get 67.7. And finally, in cell number 3, we have arc, this is, we call it B3. It's arc B in cell 3, 1.2 times 132.1, and we get 158.5. So again, you just need to come up with the conductance per unit length, which is a function of the hydraulic conductivity of the sediments, the width of the sediments, and the width of the river, and then the vertical thickness of the sediments, which, as I talked about before, you're just estimating the hydraulic conductivity, so don't get too worried about getting the exact width of the river or the exact riverbed thickness, because these are all lumped in together. And it turns out the model is not terribly sensitive to the conductance. So if you're off a little bit, it doesn't matter that much. But this is how we keep this really simple and let GMS do all the hard work of determining that length of overlap. As you can imagine, I've only shown 4 cells here, but it's not uncommon to have hundreds or thousands of cells underlying your stream network, and it literally does it in a second, all these calculations for you, so it's a great feature. Now, what about polygons? Let's suppose that we are simulating a lake with general head package, for example, and each cell in the grid overlaps part of the lake, and this cell is entirely overlapped by the lake, but it could be partially overlapped on the edge. And so the flow direction is vertical. A is the area of the cell. M is the vertical thickness of the sediments. So the cell conductance is Ka over M. And so what you would assign to the polygon is the conductance per unit area. So you just take so you factor out the A, and what you would assign is K over M. Again, you could just estimate the hydraulic conductivity of the sediments and then estimate the thickness. It doesn't matter if you're exact. Just get a reasonable estimate, and it's very easy to come up with this kind of term. And then let's suppose we have a general head polygon shown by this shape right here, and it overlaps 4 grid cells as follows. Cell 1 and 3 are completely overlapped, and cells 2 and 4 are partially overlapped. And so cell number 1, we have a conductance per unit area of 0.01. Let's say this is like a 50 by 50 meter cell, so we have an area of 2,500 meters. We then get a cell conductance of 0.01 times 2,500. Polygon number 2, the area of overlap is 832, so we just multiply that through, and so on as you go down the list there. The beauty of this, once again, is GMS computes the area for you, which is the hardest part to calculate in this equation, and all you have to do is come up with an estimate of the hydraulic conductivity and the vertical thickness of the sediments, and everything else is carried out for you. Okay, so once you have built your conceptual model and has properly assigned the conductances, the next step is to convert that to a grid-based numerical model, and there are a few steps associated with that. The first thing we do is create something called a grid frame, and the grid frame defines the location of the grid boundary relative to your conceptual model. And you can use this to rotate the grid if you need to. Sometimes we have a long, narrow aquifer that maybe goes on a 45-degree angle, and it's best to rotate the grid in that case so the rows and columns are aligned with the axes. But in this case, we just do just create a rectangle that's not rotated. So if you right-click in the Project Explorer window and select New Grid Frame, it will create this purple grid frame, and then there's a grid frame tool. If you click on that, it highlights these handles, and you just click on these and grab them, and you can move. If you click inside the grid, you can pan the entire grid, I believe, but in any case, you can grab these corners and position it. This little circular symbol right on the lower right, that's a handle you can use to rotate. So if you click on that and then drag, it will rotate about this lower left corner. So you can move things around and then reposition. And also, if you right click on the grid frame, there's an option to automatically fit it to your conceptual model, so it'll just automatically snap to the size and location of your conceptual model. And you only have to do that once it's set up. Then when you build your grid using the Map to 3D Grid command, what it does is it brings up the Create Grid dialog, but the origin and the widths are automatically fit to the grid frame. All you have to do is tell it how many rows and columns you want, and then it builds that grid in very, very quickly and easily. Then you have a grid. The next step is to initialize MODFLOW the same way we've always done. You can right-click on the 3D grid and select New MODFLOW, or you can select New Simulation command in the MODFLOW menu, and that will bring up the dialog where you select whether you're going to do steady state or transient, and what packages you want to use. By the way, in general, for the optional packages, you don't need to select your packages. They'll automatically be turned on based on the contents of your conceptual model. But you do need to indicate which version of MODFLOW you're using, a few other general things. And then the next step is you use what's called the Activate Cells and Coverages command. What that does is it looks at your coverage that has that toggle turned on that says Use to define active model area, and it will overlay that with your grid, and anything that's outside that polygon gets turned off. Everything inside it stays on. For some boundaries, if it's even just partially overlapped, it stays on, and other boundaries, no flow boundary, it has to be mostly inside to stay on. And so it properly activates all of the cells that should be active. And then finally, the last step in this whole process is you select what's called the Map to MODFLOW command. And what that does is it takes the features in your conceptual model, the coverages in your conceptual model, your rivers, your wells, your general head boundaries, your specified head boundaries, your hydraulic connectivity, all that is then overlain on the grid, and it assigns the cell-by-cell values. It does the conductance conversion we just talked about. It linearly interpolates things like the stage of the river bottom elevations, and again, the beauty of it is it just takes a second, and it builds it. And then later, if you want to change your model inputs, theoretically you can select the grid cells and change it, but it's much better idea to go back to the conceptual model and edit the properties on the conceptual model, and then just run Map to MODFLOW again. And in most cases, this completes the conceptual model, although sometimes there are still other things you need to do, like the interpolation option we talked about, where you interpolate your MODFLOW elevations from scatter points. You need to do that at some point in here if you're using the interpolation option. But again, the idea is that you define everything independent of the grid resolution, and then it'll automatically build your grid, activate the cells, assign all the properties for you. And that is the conceptual model approach. Now, we've covered a lot of things, and like everything else, the best way for this to be reinforced is through repetition. And so in class, we're going to build several models using this conceptual model approach. You'll get a chance to go through some tutorials and do your homework assignments related to this. And so this will begin to become second nature as you do it over and over again. And that's it. Thank you.